topic which we have to see. Obviously, I'm looking at the parallel that you have read the first slide also, and if you're not, then you would be reading this before next quiz. And before even the quiz, we will have another discussion. Do not worry that, okay, sir has asked that there will be quiz. So that means if I have any query, then there will be no point of discussion. We'll discuss before the quiz. Okay, whatever queries you have. See, the mandate is you should be aware of certain little fundamentals that you would need for getting more advanced concepts later on in the class. Okay, so in this segment, that means in GNSS principles, we would discuss about the basic introduction. We will discuss about the basic GPS signal structure, the GPS codes that I've discussed. Even before starting these 1, 2, 3, 4, 5, 6, 7 kind of headlines, let me just again reiterate the summary. So, because you should feel connected with the today's content. For that, you need to understand that. Let me just start this recording. Okay, thank you. Somebody has started it. Okay, so what I'm trying to say is that satellites are moving in the orbits in the space around the Earth. Okay, that's their job which they are doing, and they are transmitting the signals at regular interval, and they have the atomic standard clocks, in fact atomic clocks on board. Okay, when we are saying that they are generating signals, who are responsible factor for generating those signals? So in fact it is the oscillators. That means that oscillator inside that atomic clock is the prime responsible factor for generating those signals, generating those carriers, generating those codes, etc. Okay, so it is being generated by the satellite itself. It is programmed to do so. Okay, how, we will discuss that. And these signals, okay, these signals are being transmitted to Earth without any delay or so, regular interval. You as a receiver, you go into the field, you have a GPS receiver in your hand, and you receive those signals. Okay, when you receive those signals, the signal has certain information. It is a carrier, and the codes are modulated over this carrier. The carrier is modulated with codes and navigational message. The codes are nothing but they are ranging codes. They are gold codes. Just to make sure that if your receiver wants to calculate the pseudo range or the distance between receiver and satellite, it can do so with the help of the time travel estimation using those codes. And second, since the basic principle of GPS is a space resection, you need satellite coordinate also. That is given by the navigational message. Why signal is so complicated? We will see that the reason is simple, that to avoid intentional jamming of the signal, or to avoid any possible threats to GPS working from unknown or unwanted people, that's why the signal is being little complicated. Okay, and that's why principles of position fixing with GPS. The code based positioning is pseudo ranging. Then satellite is transmitting the carrier, and over which the codes are modulated. So carrier information can also be used for positioning. So one, you are using code based positioning, another is phase based positioning. Okay, and third is point positioning and differential and relative positioning. So we will discuss these aspects a little bit apart from understanding the application and GPS receiver. Okay, we will also see the types of GPS receiver and structure. Okay, so in this GPS principle concept, you can see this from this slide, that at least 4 satellites are required to solve your 4 unknown parameter. Just understand, The four unknown parameters are written as latitude, longitude, height, which you know that they are nothing but computed from with the help of some ellipsoid, the lat long and the ellipsoidal height, plus the receiver time offset. Now, please remember that as I've told you that the satellite have onboard atomic clocks. They have the very precise oscillators that is on board. What you can do is that you can not always have the atomic clocks in your receiver, because nowadays receiver has to be cheaper. User cannot purchase a crore rupees of receiver. It has to be somewhere readily available through his normal purchase. So nowadays receivers are available of $1 to $2 only. The chips are available. So, but that receiver doesn't have a very high precise clock. The clock is of quartz clock or lower quality clocks. So they will have certain offset with respect to GPS time, because GPS time is very precise. It is meant to be in line with the atomic time. Okay, so GPS time is very precise, and your satellites are having onboard atomic clocks, but your receiver doesn't have that standard, the atomic standard clock. So it will have a certain time offset, that is a large time offset from the GPS time. Now you must have seen the GPS time also in the when we were discussing about the when we were discussing about the GPS time. Okay, so let me just stop it for the time being and share the Google tab, which you just see it. Okay, so you could see that GPS time is having its recording as per their standards, and this atomic time and UTC have this leap second difference, which is very obvious. But as you could see that even GPS time and TAI have an offset. And this offset is of 19 seconds. This GPS time and atomic time has offset of, ये देखिए लिखा है ना, this. So there is your local time, then there is a UTC time, then there is a GPS time, then there is a atomic time. Okay. So let me just again, local time is the date time reported by your PC. If your PC clock is accurate to a second, then the other time scale displayed above will also be accurate to be within second. GPS time, global positioning system time, is the atomic time scale implemented by the atomic clocks in the GPS ground control station and the GPS time itself, or GPS satellites themselves. GPS time was 0 on 6 Jan 1980, and since it is not perturbed by leap seconds, GPS is now ahead of UTC by 18 seconds or so. Okay. Then TAI is Temps Atomique Internationale, is International Atomic Time Scale based on continuous counting of SI second. TAI is currently ahead of UTC by 37 seconds, and TA is always ahead of GPS by 19 seconds. And UTC is Coordinated Universal Time, popularly known as GMT or Zulu time, local time difference from UTC by the number of hours of your time zone. So GPS time is the atomic clocks installed in GPS ground control stations and the satellite itself. So they are being used as a standard or a reference to maintain your own time. Okay. So GPS time is the reference for GPS positioning. So that's what I'm saying. So that, let's say GPS time is this. This is your GPS time. And in satellites, you have atomic clocks. In receiver, you have quartz clock. So what is the offset? Offset would be less for GPS satellite clocks, and offset would be more for receiver clocks. Why? Because it is, although it is atomic clock, although they are atomic clock, but please remember, satellite clocks are in the orbit. They are moving with a very fast speed. So when clocks are launched to space and when they are away from the satellite, from the Earth gravity, they appears to move faster. So, but the atomic clocks have been prepared such a manner that these effects are minimal, but because of various type of forces acting over it, various type of forces acting over the satellite clock, there is a drift, or there is a slight drift in that clock, and that drift is properly recorded by the GPS satellite. Okay, these drifts are sent to you through navigation message by certain parameters. So what I'm trying to say here is that although GPS time is very precise, but GPS satellite clock as well as receiver clock will have offset with respect to this standard GPS time. And that offset for satellite clock would be less, but for receiver clock, it would be more. That's why in the case of GPS positioning, apart from reading your so-called you know latitude, longitude, and height, would also have another unknown parameter, which is receiver time offset. Now somebody could say, sir, why not satellite clock offset? Because satellite himself or satellite themselves, they inform you about their time offset. That is the advantage of having atomic clocks, that they will provide you the offset, that what is the offset to their satellite clocks with respect to GPS time. Okay. So basic steps are required to obtain these coordinates are: all GPS satellites have synchronized atomic clock as timekeepers. Coordinate of all satellites are known precisely with the help of system control. These satellites act as a moving control station, as I've told you earlier also. Satellite coordinates and time signals are transmitted to ground receiver. These signals reach to the ground delayed by distance traveled. Making use of simple resection principle and the range information to its satellite, the receiver computes its coordinate. Okay. So you can just read once this slide and try to understand and grasp the just read from very comfortable point of view. You should understand this concept. It's very essential also, but you take your time and try to understand the concept. Hello. Sumit, I've shared another basic slide. Is it available to you? That is little more with graphics, so you would better understand. Is it visible at your end, or
Where is it, sir? Is it in class material?
no, 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 no? I'm just sharing it. Just wait a second. It's a very good classroom lectures by University of. Let me just see which university is this.
Visible, sir. It is visible, sir.
Uh, it's UPC Milano. There is a Polytechnic Institute in Milano. So, in fact, you will have a GLab software also that you will access in this laboratory. So, this intuitive approach on GSS processing, I usually teach this basic concept from this basic slide. So, this is a ship. This is your ship. You want a position of this ship. So, this is the fundamental principle that previously ships were detected based on some radar using this simple observation is that a ship determines its location from a set of lighthouse or set of lighthouses that send an acoustic signal at a known time. So let's say they have transmitted one signal, it reflected from this, and it will go in all direction, and when it reflect back, it will understand that the the object is in this periphery somewhere. Okay, so knowing the emission time t naught in the lighthouse and the reception time of the reversed echo at t1, the travel time which is multiplied by t1 minus t naught multiplied by velocity of the acoustic signal, the rho or the pseudo range is computed. Okay, now with one lighthouse there is a whole circumference. Okay, the whole circumference would be there with the possibilities of the solution. True, very true. Similar to GPS, if there is only one satellite in the space and it is giving you the signal, you can be anywhere in its range of parameter. Okay. Another lighthouse. With true lighthouse, there is a possibility that you could be in two positions of intersection, one at upper, one at bottom. But one of them is not a C. Obviously, by hit and trial, you can estimate it. But what if you have a third lighthouse? Then this intersection would result in one single solution, which is the intersection of all three echoes, range of echoes. So except the solution would be like this. Similar to this concept, you would be having errors also because the range measurement with the help of signals would be erroneous if the time of travel estimation of the or the time difference between t1 minus t naught is erroneous. So the ranges are measured by means of traveling time of the acoustic signal from the lighthouse to the ship. Hence, the synchronization errors between the lighthouse and ship clock will degrade the positional accuracy. So if your clocks are erroneous, that means clock of this, clock of this, clock of this, that means red, blue, and green. If the clock at these positions are not synchronized, if it is not synchronized, what will happen? The error will create the zones of possibilities. So you could see the error is created by three different light bold circles, a pseudo range or apparent distance due to clock error. Although the true range is this, but you can never find the true range because you can never estimate that there is no error in the clock. Clock is always erroneous. It is a possibility. The possibility can only be reduced if the clock at the satellite end or clock at the lighthouse's end could be atomic clocks, and the clock at the ship end is quartz clock. So this triangle of uncertainty, that is the pink triangle, that is the uncertainty triangle, you could minimize this just by replacing the atomic clocks at the ship at the lighthouse end, because at the ship end you cannot equip every ship with the atomic clocks. You can equip the lighthouse with the atomic clocks, but you cannot equip every single ship in the world with atomic clock. That will enhance the cost. Similar concept is being applied to your GPS one. Summary: the position system is based on to know the coordinates of the lighthouses, to know the ranges from the ship to the lighthouses, to solve a geometric problem. What is geometric problem? Three ranges are there, that is your observation. Three unknowns are there, X, Y, Z. Now, similar to that concept, satellite broadcast orbit and clock data, which can be used. That means the line which I'm reading here, that means satellite broadcast orbit and clock data can be used to compute the satellite coordinates and clock offset, as I'm telling you in the previous slide, that although satellite clock is atomic clock, but itself it has certain small component of error, certain millisecond kind of error, but it has to be estimated. Why? Because if you do not estimate the clock error very precisely, what will happen? It will convert, multiplied with the speed of light, you will be huge range error that you do not want, isn't it? So satellite clock and clock offset needs to be computed very precisely, because that is the backbone of any navigational satellite system. That is the backbone of GPS, any kind of GNSS. Receiver measures traveling time from satellite to receiver and thus computes pseudo ranges. Why they are pseudo ranges? Because there is a lot of error involved in the distance measurement. Not only the time error, not in the clock error, but also the signal is traveling from 20,000 kilometers away from you. It has to go through a lot of medium. It has to reach to you at the user designated place. It has to go through a lot of disturbances. So that's why this error is not true error. This range is not true range. It is in fact pseudo range. That pseudo range you will get P not from one satellite, but use of 3 satellite to get the XYZ. But since I was telling you that your clock in the receiver is also subgraded, it is substandard. So what you want? The clock offset of the receiver clock has to be estimated also at the same time. So for that you need 4th satellite. So when you have 4 satellites, 4 pseudo ranges, you can solve for unknowns having the so-called geometric problem. You can solve it. How? For that you have read all dedicated course in the previous semester of least square adjustment. Once again, how GNSS work? We are somewhere in this sphere if we are using only a single receiver. Sorry, single satellite. If we are having 2 satellite, you will be a cross section of 2. Then you would use 3 measurement, put us at one of the 2 points. Okay, one of the solution is not on the Earth surface. Okay, with this you get. So lesson 1, what we learned or what we are going to learn is GPS measurement and its combinations. So measurement ranges, pseudo ranges, are computed from the traveling time between satellite and receiver. Several error sources affect these measurements. In fact, one dedicated class would be there on the error budget that we will take. In the bottom here, you have a very good figure, is that this is the satellite signal which has been sent by the satellite. This is the replica of the same signal which is generated inside receiver. There is a dedicated theory behind it. We will discuss it, how the replica is generated, what is the need of the replica to be generated, how this time of travel is estimated, but that's you need to wait a little bit. But that is the concept behind it. And using these two codes, you can have a full dedicated correlation when you get the maximum correlation phenomena, and at that time you can estimate the time of travel. Okay, lesson 2, the satellite location, which you need to learn how to get this coordinate of the satellite from the data which is being given to you by satellite. The dedicated lab would be there on this computation of GPS orbit. A very good lab. You could solve a lot of basic MATLAB code. You could write very basic small MATLAB code. You would be writing to get the satellite coordinates, and it's very wonderful job to attempt. Okay, please remember, do not copy the MATLAB code just for the sake of submitting your file, lab file. I mean, I would be least impressed with that. And in your Viva, if I ask you to open your MATLAB, write small program, and you would face a lot of trouble at that time. So better you start working on writing your code, understanding your code. Okay, that's the objective here in the lab. So satellite coordinates and clock offsets are computed from navigation message. Okay, there is a Fortran code is written .orbit.f from these wonderful scientists from Gauge. Okay, and this is the GPS navigation format. So first, lesson 2 is we will see the GPS orbit in clocks. Lesson 3, the GPS measurements and modeling. What do you mean by modeling? See, your signal is getting or traveling from 20,000 kilometer distance away. So it will be affected by atmospheric propagation, relativistic effect, clock and instrument and delays, total hardware delays. They are modeled and they are removed, and the navigation equations are built. And these equations, you won't believe that what these equations are. These are equations are your 10th level, 11th level geometry equations. See, these are the equations. Now I have given one task in your previous semester, that to find the unknown point with the help of known point, you have to write the observation equation model. You can write it down. You can write it down very easily. These are nothing but the linearized version of distance equation between 2 points. These are nothing but the linearized version of the distance equation between the 2 points. That's it. So these are the navigation equations that are being prepared. The geometric problem is linearized, and weighted least square, weighted least mean square, or Kalman filter are used to compute the solution. You know about these two. There's no problem in that. So lesson 4, 5, and 6 is the code and carrier phase differential positioning, floating and fixing ambiguities that we will do. So this is a very basic, simple concept building slide that you should. I'll share that also. No issues in that. Okay, but you understand this. Any questions from that? Any questions?
Sir, one thing that at in fourth point, it is written that ground delayed by distance traveled means, sir, after getting the signals, we have to remove those errors also, which comes due to the lagging, these distance
No.
travel lagging.
See. The problem is the in the fourth point, these signals reach the ground delayed by distance traveled. This point, na?
Yes, sir.
So what is really happening is that because when you are traveling through a lot of hindrances, what will happen? Your signal get delayed. So it's like you started from your home to reaching college, but in the meantime you are distracted by a lot of things. You were expected to reach at 9 a.m., but you were reaching at 9:15. So that 15-minute delay happened because of the lot of disturbance in between. Similar thing happened with the signal also. It get delayed by certain fraction of second. Okay, that fraction of second which is delay we consider is a time of travel. So the delay which has happened in the fraction of seconds from destination to destination, your satellite to receiver end, that total time of travel we compute irrespective of the delayed region, whatever the region happened. And using that time of travel estimation, we compute the ranges. Now these ranges have component from lot of disturbances like atmospheric, satellite clock, these are etc. The major component of error is clock delays because of the satellite end. We remove this. Okay. Another component is because of atmospheric nature that can be modeled, or you can assume at very negligible and you can reduce it. We will discuss when we discuss the error budget, the reason why to ignore or assume that the delay by atmosphere is minimum, and we ignore that because the nature of the order of magnitude of those error is not more than 6 meters or 10 meters. So we understand that, and we try to raise the number of observation. You understand this concept from your GDP. As you increase the redundancy, you would be less prone to errors or less prone to errors in your final observation. ये आलोक क्या शेयर किया आपने?
सर अभी जो आपने स्लाइड में दिखाया उसी का एनिमेशन वीडियो है वो।
ओके, चलिए इसको आप देखिएगा, जो भी आपको अच्छी वीडियो लगा है आपस में शेयर करिए. Okay, anyways, so I hope this basic principle of GPS is clear to all. I mean, this is the conceptual understanding is this. Anybody would be asking questions from you. Shivam, is it okay to you? Can you explain it to me again after reading these? Shivam, are you there in the class?
Yes, sir.
हाँ, बता पाएंगे जो पढ़ाया गया अभी तक?
No, sir.
फिर क्या पढ़ रहे हैं आप? वैली शेट्टी, आप बताइए. Hello. Yes, you are audible. Just speak. Hello. Am I audible to you? Your voice is not coming, Valley Shetty. Your background noise voice is coming, but your voice is not coming. Anyways, she doesn't want to speak. Second is, this is the basic GPS equation that we just have seen in the previous slide. Now you need to identify the problem in these equations. Just look at these four equation that is written: PU1, PU2, PU3, PU4. What is the problem in the equation that you can see? बताइए आलोक।
सर इसमें ये CD2 जो है इसमें तो दोनों जो ऑफसेट था इंक्लूड कर लिया है, तो सर मैं मुझे नहीं लग रहा सर कोई प्रॉब्लम है इसमें।
वही तो मैं पूछ रहा हूँ, सोचिए तो प्रॉब्लम क्या हो सकती है। प्रॉब्लम ये है कि जो स्क्वायर रूट है वो CDTU के ऊपर भी है।
यस सर, सीधा डिस्टेंस होना चाहिए था ऑफसेट की तरह।
एग्जैक्टली इसीलिए तो कह रहे हैं आप लोग थोड़ा सा वो अटेंटिव रहिए। इससे क्या रहता है, पता चलता है कि हाँ आप देख रहे हैं। तो डिस्टेंस इक्वेशंस के ही ऊपर आप स्क्वायर रूट रखिए, CDTU को अलग रखिए, ठीक है। बाकी तो सब बेसिक इक्वेशंस हैं। They are just written meant for a simple concept building exercise to how the equations will be written. It is expected that you should write these equation on your notebook also. That will help us in understanding the equation building concept later on. When we in the next slide, I'll explain you the equation build up that will help you. So basic navigation point position can be calculated like a resection in which satellites are orbiting. They are moving control points or dynamic control points. The range vectors are measured to each of the satellite using a time dependent code based on the time of transmission and receipt of signal. Since these times are based by a common amount due to offset between the satellite and receiver clocks, they are called pseudo ranges. Very important point. Range vectors are computed or measured to each of the satellite using a time dependent code based on the time of transmission and receipt of the signal. That we learned, that's okay. Since these times are biased by a common due to offset between satellite and receiver clocks. They are called as pseudo ranges. And pseudo ranges measured from 4 satellite are needed to estimate the user position and corresponding receiver clock bias. Okay. So that again discussion point which we discussed. Is there any question? Because I'm not getting the answers from all of you. Yashovardhan.
यस सर
हाँ बताएं क्या प्रॉब्लम है, समझ में आ रहा है?
यस सर पार्शियली आ रहा सर कंप्लीट सर एक बार रीड करना होगा।
क्यों नहीं आ पा रहा? अभी क्यों नहीं आ पा रहा है? क्या प्रॉब्लम आ रही है? बताइए, प्रॉब्लम बताइए आप। सुनील, प्रवीण, आप लोग बताइए।
Hello, sir.
हम्म
Sir, whole slide is not read one time. And overview, sir, मतलब ऐसे समझ में आ जाता है, लेकिन जब सर पूरी स्लाइड नहीं एक साथ में पढ़ पाते हैं, तब तक मतलब 100% नहीं क्लियर होता। एक बार स्लाइड पढ़े होते हैं सर, उसके बाद क्लियर हो जाता है।
तो हाँ, तो वही ये जानने की कोशिश हो रही है कि कब पढ़ेंगे वो स्लाइड पूरी। गूगल तो नहीं कर आंसर आप? कुछ के क्वेश्चन गूगल तो नहीं करते हैं? भगत कुमार।
यस सर।
बताइए, कॉन्सेप्ट समझ में आया आपको?
सर अभी तक क्लियर है।
अभी क्लियर है, चलिए आगे बढ़ते हैं। Now based on this, let us discuss the signal structure. So the signal structure is something which satellites have highly precise oscillators with a fundamental frequency of 10.23 megahertz. Satellite signals are right-handed circularly polarized. Now satellites have, as I've told you, satellite have atomic oscillators. Okay, and they are transmitting the fundamental, or they are generating the fundamental frequency initially. Based on this fundamental frequency, the satellite signals are created. So your satellites have highly precise oscillators with a fundamental frequency of 10.23 megahertz, and satellite signals which are right-handed circularly polarized consist of two microwave L-band waves. L1 carrier is 1575.42 megahertz, L2 carrier 12, ये आपको memorize होना चाहिए, 1227.60 megahertz, and the CA code, the clear access or range course acquisition code, modulated at 1.023 megahertz. P code, the private, protected or precise code, modulated at 10.23 megahertz. Now this modulated at 1.023 megahertz, what do you mean by that? That means per second, these 1.023 megahertz is used word, otherwise it is millions per second. So that means per second 1 million cycle. 10.23 megahertz means 10 million cycle per second. So what do we mean by that? We are simply saying with this understanding that modulation rate, that means at this rate they are being modulated over the carrier. Per second this many chips, per second this many chips are being modulated over carrier. So it is very high because you cannot see it. 1.023 megahertz and 10.23, they are very high frequency compared to 50 hertz. So navigation message is modulated on both L1 and L2 at 50 hertz. Okay, 50 hertz is a very low rate at which the information is modulated. Why? Because these are the values, they are the information which is nothing but the values of the satellite orbit, information about the parameters of the satellite orbit, which are a value in the sense semi-major axis, semi-minor axis, eccentricity, flattening, time stamping, clock error, clock drift, and so on. A lot of things we'll discuss one by one when we discuss the navigation message. But at this moment, you understand it is the modulation information. At what rate you are modulated. Okay. So modulation means the chips which are being modulated over the carrier is 1.023 megahertz for CA code, course acquisition code, or clear access code. 10.23 megahertz for P code, private code, protected code, or precise code. Okay. Navigation message both at L1 and L2. Two different frequency to eliminate errors introduced by ionospheric refraction. Why? Because your ionosphere is creating disturbances to the signal, but it is dependent on the frequency of the carrier. It is inversely proportional to the frequency of the carrier. Okay. So when you are saying that it is inversely proportional to the frequency of the carrier, that means it is dependent on the frequency and it can be eliminated if you have a proper relationship between ionospheric error on L1 and ionospheric error on L2 can be modeled with respect to two frequencies. So we can write those equations later on, as you could realize, but at this stage you should realize that the two different frequencies are just being used in the system, in the GPS satellite system, just to eliminate the ionospheric refraction, error introduced by ionospheric refraction. It's a very beautiful figure. You should have a look at it.
Sir, why they are saying 10.23 megahertz as fundamental frequency?
Because it is the frequency which is generated by your satellite oscillators. For example, if you could say that one singer is singing at his normal pace or its natural voice, then with the instrument you are tweaking it, you are modifying it, and then releasing the song. It is similar like that. Your oscillators are generating fundamental frequency at 10.23. Now with the help of some other devices, you are generating, multiplying by 120, you are generating another, you are multiplying by 154, you are generating another, then dividing by 10, you are generating CA code, using the same SP code. Okay, so like similar concept, it is being built. Okay. So fundamental frequency 10.23. When you multiplied it by 154, you generate L1. Subsequently, the lambda, the wavelength. When you divide it by 10, you generate CA code. CA code is not modulated on L2. It is very important information. Many times student missed it. But the blank box suggests that CA code or course acquisition, civilian access code is not modulated on L2. Okay, so L2 you generate by multiplied by 120. You have P code or Y code. You have navigation message. All frequencies derived from fundamental frequency called 10.23. Apart from the navigation message, because that navigation message is being uploaded by the control segment. L1, L2 at this CA code, P code, data cycle length of 30 seconds. So this is GPS signal structure. The repetition period, which is very important, very much important, is that CA code, which is 1.023 megahertz. How a normal student look at it? 1.023 megahertz. You read it as 1.023 as Mbps, million bytes per second. Okay, so million bits per second, it means 101010 per second, 1 million chips would be there. Correspondingly, your lambda would be of around 300 meter. Period is 1 millisecond. So they are repeating after 1 millisecond. P code is a week long code. It means it's a huge code, and every week long code is allotted to a satellite. Okay. So 10.23 megahertz, that means lambda is of 29.31. The whole P code is 266 days long, and every 7 days are allotted to a satellite. But the time period is 260 days. That means after 260 days, it will repeat itself. So it's a very long code, but the first 7 days would be allotted to satellite 1. Second day, 7 days will be allotted to 7 days. So you could divide the 266 by 7 as of now. So you could see 266 divided by 7, it comes at 38. But the satellite in the space are around 31 or 29. So they are in spares, they have this code. Let's say in future 34 or 35 satellites would be there in the space. So they could allot it accordingly. So it is a week long code. That means starts at Sunday midnight, goes up to Saturday midnight. Okay. Again, you look at it, because these are the very basic information. If you are aware of it, then you can read several segments on your own from the book. You do not need any spoon feeding. You can start reading the concept. In fact, just like Alok has shared some YouTube lecture, there is, because GPS is open in last 20 years in the public domain. So there are lot number of slides are available. In fact, I will share you one a YouTube lectures, series of YouTube lectures also for your own understanding, that is given by Professor Enge from Stanford University. And they are very beautiful lecture, very small video lecture. They are not hour long or 2 hour long. They are simply 20-minute video. You listen one video, take a small break, listen another video. That's kind of videos are available. You will enjoy it. They are all available on YouTube. You can listen to it. I'll share that link to you. Okay. So characteristic of GPS signal modulation. It's very basic concept. So component is bit generation rate. CA code 1.023 Mbps or million bits per second. P code 10.23 Mbps or million bits per second. Navigation message 50 bits per second. So the bit length is 293, 29.3 and 5950 kilometers. So you could understand the navigation message is a very long information in terms of its bit length, but very crucial information. Without it, everything fails. Please understand this. Your repetition rate 1 millisecond, 1 week, and for navigation message, nothing repetition rate is available. Only it is the information. Code type 37 unique codes are available for CA code, but 37 1 week segments are available, and each week segment is given to a particular satellite. They are called as PRN codes. Carrier frequencies, CA is modulated on L1, PY is modulated on L1 and L2, navigation message both on L1 and L2. Expected minimum signal strength at the user receiver, referred to 0 dB antenna the strength of the or described as the antenna gain in decibel with respect to a circularly polarized isotropic radiator. So a very low strength is received. Minus 160 dB decibel watt is very low strength, but that is sufficient for positioning information. Fundamental characteristic, easy to acquire due to its short period and low cross correlation between different PRN codes. Thus, easy to rapidly distinguish signal arriving simultaneously from multiple satellites. Acquired before PY code so as to provide the timing information necessary to acquire the more complex PY code. PY code, more accurate and jam resistant than CA code, not available to civilian user, resistant to mutual interference when signals are received simultaneously from multiple satellites, difficult to acquire, that is receiver correlator must be timed to within roughly 1 P code chip to allow correlation. Provide satellite health status, time, ephemeris data, various corrections terms, and handover word that tell the receiver where to start the search for the PY code. Total transmission time is 30 seconds. Just have a look at this slide. It's very important slide. No, I'm not in hurry to move ahead with the content just because you want little basic concept, very fundamental concept to be very strong so that you can follow little more content if I give you some papers or some extra content. But these fundamental information is very important. Just read these segments one by one very clearly. Any questions? Any doubt on any line?
Sir, these data are fixed or they vary in in any other respect, sir.
Fixed in the sense? I could not get your point.
Sir means like which we are doing modulations on the fundamental signals, and for particular purpose like CA code and PY codes means, sir, for particular GPS signal we get all these things, particularly that like bit length is 20, approximately 293 meter. Will it be always in these ranges, or for another signal or for anything else it can vary?
Mm, I could not get your point. Uh, just
Sir, I mean to say that like the characteristics of GPS signal modulation in this, these things which whatever we are getting these values, they are particular kind of thing, means we have to do all these modulation
no. These are the signal characteristics. You are user. You do not have to do anything. You just have to use the data set. In fact, when we discuss the data set which is available to you, it is a Rhinex file. You do not have to do anything with the signal. See, what I'm trying to explain here in the class is the black box operation of the GPS. What is behind it? How do you are getting the ranges? How do you are getting the solution? When you collect the data for any GPS from a GPS receiver for any point, you are getting latitude, longitude, and height. But how this is computed? So I'm telling you the uh, behind the screen kind of story for this particular GPS.
okay, sir.
चलिए आगे बढ़ते हैं. So carriers are pure sinusoids, hence cannot be used easily for instantaneous positioning purpose, and therefore two binary codes are modulated onto them. One is CA code, another is P code. Binary code data is converted from 0 to 1 state to -1 and 1 state for modulation. Satellite coordinates and additional information is sent within broadcast data message, which is also modulated onto carriers. Broadcast data message is then modulo to addition to both CA code and P code, resulting in an inversion of code and autocorrelation function. So these are the summary. Now, before looking into this GPS codes, let me just give you one figure for the modulation which you will be using or experiencing. Now, this is a very good figure. Let me just share with you. Just a moment. I've shared on chat box. Just see that it is visible or not.
Not yet, sir.
I've just uploaded. Is it available now?
Not yet, sir.
But from my end, it is shared.
It came now, sir.
Have you seen this? So in this figure, let me just share it also to all of you.
Sir, MCPS million cycles per second.
So this figure is visible to you, Sumit, at your end?
Yes,
The
sir.
figure? Huh.
Yes,
So this in this you could see that here you could see there is a shift in the chips as the phase of the carrier wave is changing. You could see here. So the carrier, you have 1, you have 0, you have 1, you have 0. Accordingly, you could see there is a change in the phase of the carrier, the information where it is modulated. If there is no change between 0 to 1, 0 to 0, it is smoothly going on as it is. But the moment it is 1 to 0, there is a change. Okay. Similarly, you have a carrier is like this, the chips is like that. So say you have a CA code 10p code chips for each CA code. So you have CA code as 1, then 0. So you could see there is no change. The moment it is 1 is changing to 0, there is a shift. So this is for CA code. Comparatively here, this is a P code. So from 1 0 1 0, so A 1 2 3 4 5 6 7 8 9 10. So there are 10 chips corresponding to one chips from CA code of P code, because the rate is 10.23 megahertz. So here you see there is a change in the phase. Okay. So this change in the phase is being attempted the moment there is a change in the code characteristic from binary in this from 0 to 1, 1 to 0. So carrier is shown here. 2 cycles per P code chips. There are actually 154 cycles per P code chip. So this figure I'm again sending to you. You can go through this figure. Okay. So 10 P code chips are there. Here you could say chipping rate is mentioned, length per chip is mentioned, repetition period is mentioned, L1 carrier is mentioned, fundamental frequency is mentioned, everything is mentioned. So carrier is shown here at 2 cycles per P code chips. There are actually 154 cycles per P code. That's true, because both are at same rate. So this is P code, and at the CA code is only modulated onto a 90 degrees phase shifted version, that is quadrature component of L1. Then before the modulation, the code chips are converted into code state. That means either they will be +1 or -1 by this formula 1 minus 2x. So you can start reading the Sieber book and try to prepare your notes, and